class today? Today is first class after midterm. So we are moving into new area. So until last week, the problem we tried to solve was AX is B. Try to solve this linear equation, right? Linear equation. So we knew that sometimes we have one unique solution. So we know how to solve that problem, right? Sometimes we have many solutions. Like infinite, right? So in that case, like when null space is not zero. So we try to find what's the dimension of null space. Also try to find out special solutions, right? Then combine the particular solution. Then okay, this is total solution, right? Last case is no solution. There is some cases we don't have any solution. So Kwakujin, when you have no solution, are you going to give up? So what are you going to do? No solution. So what are you going to do? Actually, we try to get approximate solution. These solutions are exact solution. Okay, this is approximate solution. So that's the problem we try to solve. Okay. So we have some example. Okay, last time we just this is whatever this is, whatever those weight. We had some example for this, right? So when you have this example, you try to come up with from this. You try to come up with set of equation, right? Okay, you have a set of equation, right? But when you measure, you come out with some numbers, right? One equation. When also it means to make measurement, you have your own measurement, right? So let's say in this specific picture, we have two unknowns. When Kwakujin have a measurement, he has from that he have two equations. It's Kwak. Okay? Then Iminsu says, I have my own measurement. So Iminsu have another equation, Iminsu. It's possible, right? But numbers are a little bit different, right? So when you try to solve this equation, now we have two unknowns and four equations. Myungjin, usually we don't have any solution, right? Two unknowns, but we have to satisfy four equations, right? In most cases, we don't have a solution, right? So what are you going to do? You just pick only two equations? Or, I don't like his equation. I just take his equation, right? You can solve that, right? Or take one equation from him or one equation from you, then solve it, right? Then just discard him, whatever, throw away another two equations, right? Even though he spent some time for measurement, right? That's better, or I try to use all equations. It's better to use all of them, right? So in that case, but there is no exact solution. Somehow you try to solve an equation which is best for this. Because here we have to assume mostly we have some measurement errors. Okay? So that's what we try to solve. Okay, before getting to that solution, we have to introduce new concept. Okay, so goal is, okay, because we know how to solve these things, now we try to handle this area. Okay, now we learned this, so we will solve this problem. In reality, we have many cases. We have many more equations than number of unknowns. Then in that case, we try to solve the problem, try to solve the approximate solution or best solution, not exact solution. Okay? So that's the main concept. Okay. First concept is orthogonality. Anybody can explain what orthogonal means? 예? 수직 or 직교, right? Sometimes you learn of it. Perpendicular, right? 직교. So this is a relationship between two vectors. This is one vector. This is another vector. V1 and V2. What's this? This is angle between two vectors, right? Okay, angle between two vectors, right? Orthogonal means this angle is right angle, 90 degrees. Okay? So in that case, we call these two vectors are orthogonal or perpendicular each other. Okay? So before learning that, we introduce just some new concept which is very familiar to you. I don't have to spend that much time here. You already learned the inner product, 내적, right? So inner product, right? To have an inner product, two matrices should have same dimension, right? Like this is 1 times n. This is U and V are n-dimensional vectors. Then UT, V is inner product, right? This concept you already learned in high school. Also, what's the magnitude of vector? Or magnitude or length? You already know that, right? So, like, it's a two-dimensional space like R2. I said this is vector, this is length, this is more direction, right? So how do you compute length? In this case, we know that this is x squared plus y squared and square root, right? So length of vector is denoted by whatever vertical 2 bars each side. Okay, then each element, you square that, then make a square root, right? The square of the length of magnitude is this, right? It's more or less inner product of same vector. That's a magnitude. Okay? So the concept is pretty familiar with you already. The length shouldn't be negative, right? This is one of theorem. If two vectors u and v, we just compute the inner product. If inner product is 0, I say they are orthogonal. They are perpendicular. Why? You may say by definition, or when two vectors inner product, or you may prove. What technique do you use for proof? Pythagoras, right? Pythagoras theorem. You already learned, right? What is Pythagoras theorem? Yeah. 피타고라스 정리. We say triangle, right? Whatever, right? This one, right? Then A and B, then C. C square is A square plus B square, right? This is Pythagoras. It only works when you have right angle here, right? Okay? So using that, we try to prove this theorem. Okay? It's pretty simple actually. This is diagram, right? This is x plus y is x. This vector x. Then when you add vector y, this is the one, right? This is right angle, right? In this case, from Pythagoras, we know that this is x squared, right? Magnitude, right? This is 2. Then this should apply, right? When you have this one is actually st inner product of x, right? This inner product of y. Then this one you can expand that. This is the two terms. Then this should be 0. Right? It's a very simple proof. So when you say if they are orthogonal, then inner product should be 0. Or if inner product is 0, then it's orthogonal, right? But that's simple proof. Another one is, what happens, this is, vector is 0, another one. Let's for example, ut, then v is, so when u is all 0, obviously this is 0, right? By definition, just any vector is orthogonal to 0 vector. But it doesn't mean that much, but in theory, right? Okay. So you have a good understanding in terms of orthogonality between two vectors. Now we try to find the relationship between spaces, vector spaces. Again, what's a vector space? Speak up. Like when you have a vector v1 and whatever v, let's say k, by combining them linearly, it comes with space, right? So whatever combined, like basically ci, vi, then all these points is more or less vector space, right? In the case of, let's say assume each one is independent, then this is k-dimensional, right? Okay, that's vector space, right? Now, so we try to define, okay, this is one is a vector space. I call it S. Okay, so another one is just is V. Let's say V and S are orthogonal or perpendicular. It means any vector in vector space should be perpendicular with V. Okay, anyone. It means, let's say this is U. Okay, any vector there, right? It means when you combine this one and U, right? If dot T inner product, right? It should be 0, right? It means usually UT all VI should be 0 for all I. Okay? So this is orthogonality between vector and space. Oops. Then also we can expand also between two spaces, like space S1, space S2. Any vector in space S1 or any vector in space S2, if they are perpendicular or orthogonal, we say those are orthogonal. Okay? Just its definition. 예, 고마워요. So many concept issue. Then we learned about four spaces. We learned about the four fundamental subspaces, right? Okay. For matrix M times N. Let's say, what's a column space of A? This is in R M O N. 이혜진, column space of A is in R M O N. 예? 이혜빈, 예. 예. M O N. Yeah. M, right? Column space, right? So each column, how many elements there, right? Right? This is RM, right? Okay. Then how to see AT? This is Rn, right? This is column space, we call this row space, right? How about the NA? This is null space of A, right? What is A? NA is Rm or Rn? N. Because now this is space for the possible X values, right? So N 곱하기 N, you might multiply it, right? This is N, right? Then the other one is this is N, A transpose, right? So when you try to think about orthogonality, their dimensions should be identical, right? So there's no way it says, okay, this is, let's say, V1 is 1, 1, 0, V2, 2, 0. There's no way to compute inner product, right? Has to be same dimension, right? Unless they are same dimension, there's no such things. But here is they are in same dimension, right? So we try to find out what's the relationship in this and that. Okay? What your claim is they are orthogonal. Okay? Also, these are orthogonal. Okay? So this is case of this row space, this row space. This is column space of A transpose. This is null space. They are in Rn. Actually, when you think of they are orthogonal. Okay? In the case it's Y, right? So I'm going to spend some time why they are orthogonal. So basically, try to find some reasoning. By certain logic, oh, they are orthogonal because of A, B, C, D, E, right? So here my claim is row space, which is denoted by column space of A transpose, is also orthogonal to null space of A. Let's think about AX is 0. In that case, all of the vectors which satisfy this equation, that's a definition of null space, right? So this one actually is row of A, 1, row 2, row n, right? This is just rewriting, this is x, right? Then when you multiply them, oh, this is row 80, row, then inner product, right? This ought to be 0, right? This is 0, right? This is 0. So, oh, this one and this one is orthogonal, right? It means row 1 of A is orthogonal to any vector in null space, right? So here is actually there's a relationship. Okay, so I don't have to. So that's the reasoning. Then when you combine them linearly, there's also orthogonal. Okay. So we say following the argument, null space and row space are orthogonal. Also, let's say we learned the rank, right? What's the rank of A? Hakojin, what is the rank of A? Yeah, when you have some row elimination, is rank is number of non-zero pivot, right? So we call R. Okay, so rank of A is same as rank of A transpose, right? This one, this is R. Okay. This is a dimension of what? Column space, right? Also row space as well, right? Okay. Then that's why it's row space is dimension R. The remainder belong to another one. It's n minus 1. So when you add dimension of row space and dimension of null space is n. Okay? So we just call them, so this orthogonal complement. Okay? Let's think about it this way. Let's give one example. This space of R3. Okay? This space of R3. Assume this is one plane. Okay? Let's say this plane, let's say R3, then we have some matrix A. Okay? Let's say this one is, let's say also this is A transpose. Okay? This is A transpose, right? But here is, I say R is 2. That's why it's, R is, let's say this NT here is 2-dimensional, right? This is n minus R, right? So n is 3, then this is 2, right? Then then row space should be orthogonal to here, right? This one should be only one line because this is dimension 2, then this should be dimension 1 because when you add them up, it should be 3. Okay? So this whole space is null space is 2-dimensional, this is 1-dimensional. So when you add them, their dimension become 3. That's why we call orthogonal complement. Okay? Still, it's a definition, just explanation. I'm going to ask some questions from there. let's say this is row space. This one is null space, right? This is null row space AT. In special case is can you tell what's this? Intersection of row space and null space for that diagram. This one. What's this? Just based on the diagram. Only zero vectors, right? Because this subspace should include zero vector, right? This one includes zero vector. This one actually is line crossing this way, right? But they only share this origin point, right? How about this? This is actually this plane plus this line, right? That's all, right? Okay. I'll ask another question. I take one vector from here, okay, u. Then I take another vector from here, v. Take a vector from here, take a vector from here, then add. Okay? Or say u times v, when you add, what's this? What's the vector space for this? Eh? Eh? Speak up. This is R3 for this example, right? This is also orthogonal, right? Whatever, right? Take any vector here, then use one vector, then when you multiply set is R3. Okay? So in this case, you can represent any the x in R3 can be represented as one vector from CAT, eh, plus one vector from null space. Okay? So that's the main concept. Okay. Also, in this case, because these two spaces are orthogonal, obviously in this case, u and v are orthogonal as well, right? Okay. Okay, this is one of example. Like for whatever A is m times 3 matrix is. In this case, let's say row space is line or null space is line. Is it possible? I just posted in this on the web page. You don't have to write. Is it possible? Myungjin, that's possible or not? if there's a line, then rank should be 1, right? If this one is line, this should be m minus r, right? From here, it says n is 3, right? It requires this one has to be plane 2, right? Line, it doesn't make sense, right? Okay, just reasoning. Or we can do similar, but so I'm going to skip this. Okay, so I'm going to, let's see, what time is it? 1:30, right? Just I'm going to make a 5-minute break, then move on to another topic, okay? Solving AXB equals 0 when there is no solution. Usually, you have more equation than number of unknowns, okay? So no exact solution. In that case, we try to find the best solution. Okay, so let's think about this example, right? This is an example I took from one linear algebra book. So when you have exact measurement, this we have two sets of equation, right? Set of equation here, right? So then you can solve it. It's great. There's no problem. But when you measure, usually into some errors, right? So when you ask, when you ask 3 people to make a measurement, we have now 6 equations, right? Right. This is whoever says is a Gauss measurement. It's a perfect measurement, right? When when you make a measurement, instead of you say it's 40, you say it's 41, right? It's your measurement, right? So all these numbers will be different, right? Then when I ask Ji-Young-Tak, you will come out with your own set of measurements, right? So now we try to solve the problem. Problem is, whoosh, we have 6 equations and 2 unknowns. We try to solve this problem, then it says there is no solution. That's what are you going to do? So we try to find the best solution. Rather than picking 2 equations randomly, then solve the problem, okay? This is very typical situation in reality, okay? Let's think about this one. You know what GPS is, right? What is GPS? Satellite, yeah, system, right? Let's say basically when you go out, when you move around, how do you determine where you are exactly? Find your location. So find your location, right? So we use GPS. Or sometimes you don't have a GPS. What are you going to do? There's no GPS. Yeah? Then we have everybody using cell phone, right? So you are here. We are still, so cell phone is a tower, right? Also antenna towers. This is location A, and B, and C. So you are receiving signals all 3 points. Okay, they are synchronized, measuring time difference in signal. Now you are able to locate where you are. Okay? This is what you use in navigation, hanghe, all those things, right? So when you have 3 points in measurement, you are able to measure your position, right? But as I said, all this one is not perfect. So measurement errors, right? Or synchronization may not be perfect. So what are you going to do? The GPS, I can use 3 satellites. Or I may say, oh, I can receive 5 of them. Do I have to use all 5 of them, or just don't worry, just pick only 3? We expect when you use all of them, it may improve the accuracy, right? Okay? So that's the problem we have here. Okay? So this is problem actually. Here is AXSB, n unknowns, and m equations. The number of equations usually more than number of unknowns. Okay? So may not have exact solution. Then we like to have a best solution. Okay? That's a formulation of problem. Without any explanation, so we try to solve x, but here we try to solve approximate solution, right? We call them x hat. Okay, rather than solving this, now we can solve this equation, then that's the best solution. Here, I do not say why. Okay, I'll discuss it later. Okay, so basically, this one is the exact solution. I try to solve it, it's no solution. Then I say, okay, I use this solution, A transpose A, X hat, A transpose B. When you solve this is almost always solvable. Then in that case, you have best solution. I'll explain later. What is A transpose A? A transpose A is always square matrix, right? Or square matrix, right? Or symmetric. Or symmetric matrix, okay? In order to solve this equation, this one should be invertible, right? G-형태, right? It's invertible, you can solve this equation, right? Not invertible, sorry, you may have some problem, right? Okay, this is one of example. A is 2 by 3. I'm sorry, 3 by 2, right? There's 3 equations and 2 unknowns, right? So A transpose A is just multiplying A transpose A, then you come up with that matrix. Then when you try to solve this problem. So A transpose A is invertible exactly when A has independent columns, okay? So once you get the information, you are solving. Okay. Let's think about this. Probably this is the one we have similar problem in exam, right? Let's say it is 3 by 2, x1, x2. When you multiply them, then this B1, B2, B3 has to satisfy certain condition, right? To solve this problem, right? So one problem is B2 plus and B3 should be 0, right? Okay. If this is not the column space, you are not able to solve problem. So in that case, actually, rather than solving, we have like A transpose AX equal A transpose with one other problem. Then we can solve the problem. But sometimes this equation, using that, but this equation, this one is invertible. Now you are able to solve the problem. But sometimes these are not independent. It's not invertible. So sometimes we are able to solve the problem. Sometimes you can solve the problem. Okay? So When this matrix is invertible, you are able to solve the problem. Not invertible, sorry. What's the condition that this matrix is invertible? Is when A has independent columns. Okay?